This video is for example 10.6.4 in Greenberg's book, and the topic of the example is calculation of the inverse matrix via Gaussian elimination procedure. So the basic idea is outlined in the textbook. So suppose you have a matrix A and you want to solve the equation AX equals B. Given the matrix A, the vector B, you're looking for the vector X, that's your problem. We can, in some sense, write this. We can write that AX is equal to the identity matrix times B. Okay, I'm always free to pre-multiply a vector by the identity matrix, and I should get back the same vector. And so the point is that we know if we make a transformation at the end of the day, we're looking for the matrix A inverse such that X is equal to A inverse B. Well, I can pre-multiply X by the identity matrix. And then the idea is we know that one way to solve this problem is to do Gaussian elimination. Alternatively, we can see that the Gaussian elimination steps that get us from the matrix A to the matrix I must be the same Gaussian elimination steps that get us from the matrix I to the matrix A inverse. So all we need to do to construct the matrix A inverse is to perform the same Gaussian elimination steps on the identity matrix that we performed on A to get it into row-reduced echelon form. So as a concrete example, let's consider the matrix 1, 3, 0, minus 2, 3, 1, 0, 1, 1, and let's append the identity matrix 1, 1, 1, 0, 0, 0, 0, 0, 0. Okay, and so the point is that when we do the appropriate Gaussian elimination steps to get this matrix into row-reduced echelon form, it turns out that the row-reduced echelon form will convert the original matrix A into the identity matrix, and it will always do this as long as A is full rank. Okay, so in this case, A has full rank. It's rank 3, which means all the rows are linearly independent, or all the columns are linearly independent, or the determinant is non-zero. Those statements are equivalent. And we see what those Gaussian elimination steps do to the identity matrix. So the first row of the identity matrix becomes 1/4, negative 3/8, 3/8, 1/4, 1/8, minus 1/8, minus 1/4, minus 1/8, 9/8. And so the point is that we must identify the new matrix, which the identity matrix has become after the Gaussian elimination steps, as the inverse. So it must be that A inverse is equal to, let's just pull out a factor of 1/8, 2, minus 3, 3, 2, 1, minus 1, minus 2, minus 1, 9.